well, it is for me a great pleasure to have today in this seminar Yuri Lima from the Federal University of Ceará. Well, he's a very enthusiastic speaker, a very good friend, and then it's always a great pleasure to have a Yuri as a speaker. And then today he will talk on Markov partition and adapted method. Please, Yuri, you can start. Thank you so much.
Okay, Lorenzo, thank you for the invitation and for the kind words. I really appreciate the initiative of having this online seminar. And I think it's only in this way that I am able to speak to more than 50 people in the audience. So it's a good opportunity to speak to a bigger audience. Even though it's a bigger audience, I remind you that you can stop me and make questions at every time you want, okay? And taking the advantage that Lorenzo mentioned, the next Friday that will be in honor of Christian Bonatti, I should also mention that next year we are going to have the version number 6 of the Brazilian School of Dynamical Systems here in Fortaleza, and it will be dedicated to the 60th-year birthday of Lorenzo himself. So everybody is invited to come to Fortaleza next year. So I'm going to start my talk now, and as Lorenzo said, I will talk about Markov partitions and adapted measures. And most of you might have heard about Markov partitions. I will not try to give the proper definitions, and instead I'll try to recall you what they are by means of pictures. But there is this new name, which is called adapted measures. And I should also say that adapted measures are not new in the literature. They have been considered before, and it's just a name for something that appeared a few times with some different names. And as you're going to see, there has been work regarding adapted measures since 1981. Okay, so starting my talk, I would like to start actually with application of the results that I will mention towards the end of the talk. So consider a classical Lorentz gas. And what is a classical Lorentz gas? It is, you consider the two-dimensional torus in which you have this fundamental domain given by this square, and you put two obstacles in this torus. You put an obstacle here in the center with radius small r, and you put an obstacle in this vertex, which appears, both obstacles are circles. So the second circle, it appears in the fundamental domain in 4 pieces like this. And on the complement of the obstacles, you consider the usual billiard dynamics, which is the dynamics of a point particle walking at unit speed until it hits one of the obstacles, in which place it reflects in a specular way and continues making this movement in a straight line with unit speed until it hits the obstacles again, and so on. So this is the usual Lorentz gas, and from the point of view of dynamics, we actually have 2 possible dynamics to consider with respect to this example. We can consider the flow associated to this, or we can consider what is known as the collision map, or as Sinai called the derived map, which is just to associate the discrete time map that to each position in the boundary of the obstacle and direction with respect to the normal direction in this point, you associate the next hitting position and the next angle of the next collision, and so on. So for the purpose of this talk, I will be talking only about the collision map. So I will not talk about the billiard flow, just the billiard map. So here it is, we will call it small f. And to provide the application of the results, I'm actually going to focus in a specific situation of this map in which the small angle, the small radius is 1/8, and the big radius is 3/8 plus some very small epsilon. And the results regarding the dynamical point of view of this map are given by this theorem in this slide, which say the following. So let us consider for a moment that epsilon is very small. So this map it pretty much looks like an annals of diffeomorphism, like uniformly hyperbolic diffeomorphism. But it has an extra difficulty given by the presence of what are called the grazing collisions. These grazing collisions are trajectories that are tangent to one of the obstacles. And when this phenomenon happens, then if you calculate the derivative of the map, you see that this derivative is going to be equal to infinity. So you see a sort of explosion of the derivative as you approach these grazing collisions. And this is a very big difference between the billiard maps and the usual annals of diffeomorphisms. And it's actually one of the reasons that makes the analysis of these billiard maps much more complicated than the usual uniformly hyperbolic dynamics for smooth systems. So first of all, it is not clear whether you could recover some sort of topological entropy by means of open covers, just like Bowen did. And in this specific situation, and actually in a wider class of examples, Baladi and Demers, this is the part one of the theorem, were able to provide a sort of Bowen-like definition of topological entropy. And they showed that this topological entropy is going to be positive and finite for this class of examples. They were also able, in a remarkable way, to show that there is a unique measure of maximal entropy, and this unique measure of maximal entropy is adapted. Well, I'm not going to say what adapted is in this moment. I'm going to leave it for the second half of the talk, but just keep that in mind. It is a measure that with respect to this set of grazing collisions has some special property. And because it has some special property, we are actually able to get the second part of the theorem, which is a joint work with Carlos Mateus, which we are able to construct a countable Markov partition that codes this adapted measure for almost every point. So almost every point belongs to this countable Markov partition. And not only that, out of this countable Markov partition, we are able to construct an extension of the billiard map in which the coding coming from the extension to the billiard map is finite to 1. So because it is a Markov partition, the extension is going to be a topological Markov shift. And with this extra property that this coding is finite to 1, meaning that almost every point below is coded only by finitely many points above, Jérôme Bouzy was able to get very good estimates on the number of periodic trajectories of these billiards. So he was able to show that the number of periodic trajectories grows exponentially fast with respect to the topological entropy constructed, shown to exist by Baladi and Demers. So this is just an application on how to use what I would like to focus today, which is my result with Carlos Mateus. All right. So in this talk, I'm going to focus on these two things. I'm going to focus on how to get good codings for this class of billiards. And actually the coding is going to be induced by means of a countable Markov partition. So whenever you see coding, you should keep in mind that it is a sort of Markov, it is a Markov partition that has countably many elements in the phase space. And this countable Markov partition, is actually constructed independent of any measure. It's constructed in an abstract way when you look at the set of points satisfying some set of conditions. So this is also similar to some previous results of Wilton on non-uniformly expanding maps, that you only look at the set of points satisfying certain properties and you get some sort of coding for them. From the point of view of measures, the measures that actually live in this coded set that we are going to be able to construct will be exactly these adapted measures that I'm going to mention in the next slides. All right, so part one is just to recall you with pictures what Markov partitions are and to provide the setup of the results that I'm going to mention in the second part. So nothing better than the cat map to remind you of the Markov partition. So you consider this classical example, which is an hyperbolic automorphism of the two totals induced by this matrix 2, 1, 1, 1. And I think that we all have seen a way of constructing a fundamental domain for the two totals in other ways to tessellate the plane by puzzles like this L-shaped here, in which the boundaries are made by stable and unstable directions. So in this specific case of linear automorphism, these directions are actually eigendirections. And they are very good because if you consider one of these pieces, which is just the two totals seen here in the universal cover, and you subdivide it into these three pieces, then you see that the action of the dynamics in these rectangles satisfies a good intersection property. And because it satisfies a good intersection property, you can actually associate each trajectory to paths on this graph. So what is this graph on the right-hand side? It is the graph made whose vertices are the three rectangles that I constructed, and the edges, they show what are the possible transitions according to the dynamics from one rectangle to the other. So because these rectangles are good in satisfying some good intersection properties, we are actually able not only to associate to each real trajectory a trajectory on this graph, but also to each trajectory on the graph, we are able to associate a trajectory of the original cat map. It is exactly this good intersection property, which is shown in this picture, which allows us to go back and forth in this association of real trajectories of your map to trajectories in this oriented graph. So in broad terms, Markov partitions are nothing but a simpler representation of the system, in the sense that you subdivide your phase space into a family of rectangles with good intersections. And good intersections means exactly what I mean in these two pictures. So the left-hand side shows a good intersection, and the right-hand side shows a bad intersection. And the difference from good is bad is that in good, whenever the image of a rectangle intersects another rectangle, it has to intersect all the way from one side to the other, of course, with respect to the unstable and unstable directions. And whenever you have this good intersection, you can get actual trajectories of your dynamical system, which are sequence of location points x0, x1, x2, and so on. And to code them, just say what is the sequence of rectangles that this trajectory is visiting. And this coding is not only good, but also good is the decoding that you get out of this. And what do I mean by decoding? I mean that if you give to me the sequence of visited rectangles, then I will be able to recover what is the original sequence of locations of points. So this is rather reasonable because instead of prescribing exactly what the point x0 is, exactly what the point x1 is, exactly what the point x2 is, you can just describe this trajectory by means of a sequence of symbols, which is exactly the sequence of rectangles that you are visiting. All right. So the models that I will consider in this talk is a subclass of non-uniformly hyperbolic models. And just to recall you might all know, but I always like to make this comparison between uniform and non-uniform hyperbolicity. I start saying that hyperbolicity is all about contraction and expansion, just like what a baker does when he's preparing the dough for a bread. He expands and contracts the dough in times. And well, in this simple example, you can regard uniform hyperbolicity by what an ideal baker would do, and non-uniform hyperbolicity by what a real baker does. In which sense? In uniform hyperbolicity, this contraction and expansion that you see is required to hold at every time of the iteration of the map, of the dynamics, and also at every point of your phase space. So imagine that an ideal baker, he never gets tired and he never forgets tiny parts of the dough. So the procedure of preparing the dough is exactly that one given by uniform hyperbolicity. But we know that an ideal baker does not exist. So it's more natural to consider what a real baker does. And in some sense, this is non-uniform hyperbolicity. Because contraction and expansion that a baker does, it only happens sometimes, as long as it happens on the average. So from time to time, the baker can get tired and he doesn't expand and contract in some moments. And also the contraction and expansion only happens almost everywhere because some small parts of the dough might be forgotten in this procedure. So non-uniform hyperbolicity is much more tailored to real examples in the real world. And this part of explain the broader applications that this definition has for concrete examples. So we will consider non-uniform hyperbolic systems, which of course include the class of uniformly hyperbolic systems. So let me give you concrete examples exactly given by the billiards. And the difference of these examples is that I will change the table in which the billiard is defined. So the first example is given by what is known as a hyperbolic billiard or a Sinai billiard. And to explain to you what the video means, it is this table in shape in some, has 4 pieces in the boundary. And the video has a huge amount of particles, each of them performing the trajectory in an independent way. So there is no interaction. And why it's better to see the video like this? Because like this, you can see the chaoticity involved in the system. So as you're going to see, you really have sensitivity to initial conditions, because although all the particles started all together, more or less with the same direction, after a while, the positions that they are in the table, they spread quite uniformly in the table. And not only that, but also the directions of the angles, which is seen by this histogram here in the circle, they seem to uniformly equidistribute in the circle. So this is exactly what we expect. Sorry? Did someone say something? No, okay. So this is exactly what you...
Sorry.
Okay, Koro. So this is exactly what we expect to see in a uniform hyperbolic system, and this is exhibited by this class of billiards, which are called either hyperbolic or dispersing or Sinai billiards. An example which is kind of genuinely non-uniformly hyperbolic, well, there are many, but perhaps the most famous one is given by the Bunyamovich Stadium. So this is given by the next video, which also tries to show to you some sort of sensitivity to initial conditions. So you have this bunch of particles all starting more or less at the same point and more or less with the same direction. And after some hits, the positions here, there is no histogram of the directions of the trajectories, but the positions, they start to equidistribute into the table. So this is exactly what we expect of this kind of chaotic systems that we want to analyze. So these 2 classes of examples will be covered by the results that I will mention in the next slides. And also, I want to cover some situations that are one-dimensional. So imagine, for instance, that you have the quadratic family. And as you know, Jacobson proved that there is a positive set of parameters for which the quadratic map associated has an absolutely continuous invariant measure with positive Lyapunov exponent. And well, we are in dimension 1, so we only expect 1 Lyapunov exponent. So say that non-uniform hyperbolicity happens in dimension 1 is exactly this. It's saying that this Lyapunov exponent is bigger than 0. So what Jacobson showed is that for a positive set of parameters, there is an absolutely continuous invariant measure, which is non-uniform hyperbolic. Well, the results cover these situations, these examples considered by Jacobson, but it also covers situations in which you can have discontinuities for the map, as long as these discontinuities happen in a polynomial-like way. So we not only allow these discontinuities to happen, but we also allow the derivative near these discontinuities to explode to infinity, as well as the derivative near critical points to converge to 0, because here it is 0. But we only allow this convergence to 0 and to infinity to happen in a polynomial-like way. So I hope that as soon as I explain the setup of this context, it will be better for you to understand. But before saying the setup, I want to say what is the main difficulty of coding non-uniformly hyperbolic systems. Here I've shown a phase space in which these 3 dots mean that this space might not be compact, although we always require that it has finite diameter. And this red curve is part of the phase space in which perhaps we cannot define the map, just like in the billiard situation, in which actually grazing collisions are taken out of the phase space because in them you have derivatives which are infinity, and this is not good to treat. So whenever you have this kind of phase space, which lives outside this curve, in which some bad behavior occurs because you have explosion of derivative, and you also have some bad behavior because the phase space can be very small in some sense, there are 2 main issues in order to do the coding. The first one is with respect to the geometry of the phase space that you are working with. Perhaps the exponential map, which are the natural charts that you analyze this manifold, they behave very badly as you approach these points at infinity. For instance, if the curvature gets very big, then the exponential map can also get very big in a very fast way. And the other difficulty is related to the dynamics itself. As you approach this red curve, perhaps the derivative can explode in an uncontrollable way, for instance, exponentially fast. So the presence of these 2 difficulties, one given by the geometry, the second given by the dynamics, show that unavoidably the choice of rectangles to cover your phase space, which is actually the fundamental question to construct Markov partition, unavoidably these rectangles are going to be somewhat like in this picture. So the rectangles are going to be very distinct sizes. Some of them will be very small. The overlap among themselves will be very complicated to handle. So there might be a rectangle here and a very nearby rectangle in which the position of themselves, the overlap that they have, does not depend one and the other. And this makes not only that the overlaps are complicated and not only that these rectangles are going to be very small, the smallness of rectangles can be given either by the bad non-uniform hyperbolicity that you see, or by the proximity to this red curve, or by approaching some points at infinity. And altogether, if you have to consider small rectangles, then in order to cover the whole phase space, you will need infinitely many of them. And that is the main reason that, contrary to the usual situation of smooth uniform hyperbolic systems, in which Markov partitions actually have finitely many rectangles, here we will need, in general, countably many rectangles to construct the Markov partition. And not only that, so this shows the difficulty on the coding, which I hope I explained to you that at first sight is complicated, is difficult. But not only that, the decoding is even more complicated. Because if you have these complicated overlaps, then it looks like, and you actually do have, a big ambiguity of the coding that is going to be in some sense unboundedly complex. And if you say that you have an ambiguity of coding, this is telling you that the same sequence can represent many trajectories. And this means in some sense that you cannot have a good decoding. So whenever you have the situation, although you were able to construct a good coding, well, as long as you don't have a good decoding, your coding is not good, because what is the purpose of it? All right, so now I will go to the setup. And before looking at this big table, the summary actually of this big table is two things. It's actually related to the two difficulties that I mentioned before. The first one is the possible degeneracy of the geometry as you approach small parts of the phase space. And the second one is the possible degeneracy of the derivative of the map, which can go either to infinity or to zero. This is basically the situation, the setup that we want to control in the two-dimensional situation. In the one-dimensional situation, we want to control that, but we also want to control in some sense the sizes of inverse branches. The set in one dimension will not be invertible, so we have to require something about the sizes of the inverse branches. So have that in mind, that the summary of this table is just conditions to control the geometry, conditions to control the degeneracy of derivative, and sizes of inverse branches. And the control that I'm going to require in these three instances is that all of the bad behavior can happen at most polynomially fast. So this is already included in the work of original work of Sinai for billiards, and it was highly stressed in the work of Katok and Strelchin also for billiards, and it's also crucial for us. So again, the bad behavior can also happen polynomially fast. Okay, so let's go to the table now. So we are going to fix some A, which is bigger than 1. And in the context of two-dimensional maps, which I only mentioned two-dimensional billiards, we are going to consider a phase space, which is a surface with finite diameter, but I do not require it to be compact. Inside this phase space, we are going to consider a subset S, which will be called the set of discontinuities. So in the context of billiard, this will be given by those grazing trajectories and also by the possible breakpoints that you have in the boundary. So whenever two obstacles intersect, their intersection might give rise to a breakpoint, which is a point in which the curvature in the boundary is no longer C2. So putting these two possible phenomena together, we consider this set as the set of discontinuities. So the geometrical assumption that we require on the phase space is that the exponential map is well behaved in a neighborhood of a radius, and as you see here is a radius that is, it can be very small, but it cannot be very small. It can be only polynomially small with respect to the distance of the point to the singular set S, the set of discontinuities. So in the two-dimensional situation, we only consider invertible maps. So each point has at most one per image that is defined in the complement of the singular set. And now comes the condition for the dynamics, which says exactly what I mentioned in the beginning. We require that the derivative, yes, can explode as you approach this set S, but it can only explode or go to zero, the derivative in its inverse, polynomially fast with respect to the distance to the singular set. So this is the philosophy of this inequality here. And the situation for the context for one-dimensional maps is very similar. Well, it's one-dimensional, so we can consider the phase space as the interval 0, 1. And in this case, the set S that we are going to consider outside of the phase space will be given not only by the discontinuities, but also it will include all the critical points associated to it. In the interval 0, 1, we exponential maps are all identities, so they are automatically as regular as we want. And here is the difference when you consider non-invertible situations. So as I said, you have to control in some way how good or how big the inverse branches are. And we require that these inverse branches are good and well-defined, well-behaved, in a radius which is at least as big as this minimal here. So you consider the distance of the point and of its image to the singular set, you raise to a power a, and then you require that the inverse branch that takes f of x back to x is well-behaved in this neighborhood. And finally, again, we require that the derivative can either explode to infinity or to zero, but only in a polynomial fashion. All right, so this is the setup. So in part 2, I want to mention what is the set that we are going to be able to construct this Markov partition. Finally, I will mention what is adaptability, which translates to the point of view of measures, this coded set that we are able to code. And finally, I will mention the 2 results of the talk. So the coded set, first of all, it depends on a fixed parameter chi. So we are going to fix a parameter chi, and we are going to look at points with 3 properties. So this is actually a rough sketch of the definition of the coded set. The proper definition, of course, it demands more specific explanation, and it actually requires some more conditions. But in summary, they are all related to these 3 properties that are in the slide now. The first one is that you look at the points with some non-uniform hyperbolicity at least chi. The second of all is that because you have this singular set and things are getting degenerate, are getting bad as you approach the singular set, we want to look only at trajectories that do not approach the singular set exponentially fast. So just a remark that this fancy S is exactly the non-fancy S of the previous slide. So it's the set either of discontinuities or of discontinuities plus critical set. So this is the second condition. We will only look at points which do not approach the singular set exponentially fast. And why do we do that? Because the philosophy here that we expect is that as long the trajectory does not approach as exponentially fast, the degeneracy of the derivative and of the exponential maps do not happen exponentially fast. And so hyperbolicity, which is some sort of exponential fast phenomena, will prevail over the possible degeneracy of proximity to the singular set. And finally, we also require some sort of recurrence. I remember that in the first talk of this seminar, Stefano Lusato said that it's nice that all constructions of Young towers and kind of symbolic constructions that are available in some sense, in some way or the other, they use some sort of recurrence. And we also use this in an essential way. Being more specific, non-uniform hyperbolicity in the 2-dimensional situation in which we have 2 Lyapunov exponents is somewhat related to 2 inequalities. It is the existence of 2 directions in the tangent space, EU and ES, for which these sums are finite. Well, this is something that's related to the definition of Lyapunov exponent. You know that if the Lyapunov exponent in the EU direction is bigger, for instance, than minus chi, then this sum is finite. But the sum can be finite even in situations where the Lyapunov exponent is exactly equal to minus chi. So in some sense, requiring that these sums are finite is a looser definition than requiring that the Lyapunov exponents are bigger than chi and smaller than minus chi. So the requirement of this non-uniform hyperbolicity, which actually should be here greater than or equal to chi in some sense, is requiring the existence of these 2 directions for which the sum associated to the unstable direction is finite, and the same for the sum associated to the stable direction. And if you think a little bit, what this sum can give you is some sort of measurement of the quality of hyperbolicity along these directions. And why do I say that? Well, I say that because if EU is a bad direction for the unstable hyperbolicity, what do we usually mean by that? We usually mean that bad hyperbolicity in the unstable direction in the non-uniform hyperbolic context is when it takes a long time for you to see the contraction in the past to occur. And if it takes a long time for you to see the contraction in the past to occur, then for many iterates, for many indices, terms of the sum, this number here is going to be big. And automatically this sum is going to be big. So in some sense, the bigger this sum is, the worse the quality of hyperbolicity in this direction you have. Okay, so these numbers are good to measure the quality of hyperbolicity. Okay, so this is the first condition that we impose in the coded set. The second condition is,
the condition still implies that the exponent is larger than chi minus epsilon.
yes, it does. At least the lim sup or lim inf, it doesn't take by the existence of limit. Okay, so property 2 is self-explanatory. So you require that when you measure the distance of the iterates of the point to the singular set, and you take the log, 1 over n, this value goes to 0. And property 3 is in some sense more technical because it actually depends on a bunch of parameters that I would need to introduce, but I would just explain it in broad terms. The recurrence that we require is some sort of return to a same passing block infinitely often in the future, and the return to a same passing block, perhaps different from this other one, infinitely often in the past. So again, the requirement of recurrence is actually the existence of two passing blocks for which the future trajectory visits one of them infinitely often in the future, and the past visits the other one infinitely often in the past. All right. And well, finally, I'm going to say what an adapted measure is, which is somehow related to this second condition that we require, that the trajectories do not approach as exponentially fast. And we say that an invariant measure is going to be adapted if this function, log of the distance of the point to the singular set, is in L1 of the measure. And if it is in L1 of the measure, we are automatically, almost every point satisfies property 2 in the definition of the coded set, because this is just an application of Birchhoff's ergodic theorem. So if mu is adapted, then 1 over n log of this distance is going to 0 mu almost everywhere. So this says that from the point of view of measures, all adapted measures sit inside this candidate for coded set M0. And not only that, but also in our context in which you have a control of the derivative, whenever you require adaptedness or adaptability, I don't know what is the right way of saying that, then log of the derivative is going to be in L1. And so we can apply Ozalada's theorem. And finally, we could, for instance, say what is Lyapunov exponent, claim that they exist almost everywhere, and so on. So it seems that this adaptability condition is the good definition in terms of measures for considering inside the coded set M0, and also in our context. And as I told you in the beginning, this definition is not new. It appeared in works before. So I'm going to give you some examples where this property holds. For instance, if the Lebesgue measure is invariant, so if you have mu as the Lebesgue measure, then this perhaps goes back to Sinai, which shows that whenever you know what is the size of neighborhoods of the singular set, then you can prove that the measure is adapted. He used this in a crucial way to get his results for Sinai billiards, for dispersing billiards. The second occurrence of this kind of condition appear. I should also, before saying that, I should say that this all of these examples, it's just a subset of the examples in which this condition actually appears. So there are many other examples in which this condition is considered. Okay, so going back to the examples, the second one is by Le Drapier, 1981. He considered one-dimensional maps. I think that they were actually multimodal maps, so he did not allow discontinuities. And he defined basically the definition of adaptedness. He called them non-degenerate measures. And in this, in the same context of multimodal maps, Chititsky in '93 was able to show that whenever all critical points are polynomial-like, then every invariant measure that is not supported on an attracted periodic orbit is actually adapted. The fourth occurrence of this notion, which is related to this notion, is in a joint work of Omri Sarig, in which we construct Markov partitions for non-uniform hyperbolic three-dimensional flows that are non-singular, so they have positive speed. And for that, we construct a Poincaré section, and we want to analyze the Poincaré return map. And we look for a Poincaré section that satisfies, for the Poincaré return map F, satisfies exactly that the convergence to the singular set does not happen exponentially fast. We were able to show the existence of such section. And finally, and this is related to the first slide of the talk, Baladin and Demers, in that specific class of examples, were able to show not only the existence of measures of maximal entropy, but only that they are adapted exactly in that context. And it's exactly this reason that allows us to apply our result and get the coding for these maps. Okay, so the results finally are two. One of them deals with the two-dimensional situation, the other one deals with the one-dimensional situation. And to better explain it, I need to introduce this set sigma sharp. So what is sigma sharp? If you have a Markov shift with countably many symbols, sigma, the shift action is the small sigma, then you can consider a subset of this symbolic space, which is in some sense the counterpart of the recurrence condition that I imposed with respect to passing blocks. It's saying that the sequence is recurrent if you have two symbols, V and W, such that this trajectory visits V is equal to V infinitely often in the future, and it's equal to W infinitely often in the past. So this is exactly the symbolic counterpart of that condition of recurrence that I mentioned in 2 slides before. And the result, that is joint work with Carlos Mateus, is that in that two-dimensional setup that we explained to you, if you fix a chi bigger than 0 and consider the subset M0 that we define, then you are able to construct a countable Markov partition. And not only that, this countable Markov partition induces a finite one extension, which is going to be onto this coded set M0. And also, if you restrict itself only to the recurrent sequences, then this map is actually going to be finite to 1. So this is rather satisfactory because the sigma sharp is defined only in terms of recurrence. So whenever you have invariant measures are supported on the set. So the idea here is that if you have this good coding and you have a measure below in M0, finiteness to 1 allows you to lift this measure to the symbolic space, thus obtaining an invariant measure in the symbolic space. And also finiteness to 1 also allows you to say that this lifted measure has exactly the same Kolmogorov-Sinai entropy as the initial measure below. So because of this finiteness to 1 condition, we are able to obtain some properties from the point of view of counting periodic points or proving ergodic theoretical properties of equilibrium states and so on. So this is the result in 2 dimensions.
Can you say what M0 is again, please?
So M0 is a set which is more complicated than what I put here in the slides, but it's a set defined in terms of 3 conditions. You look at the points which have some sort of non-uniform hyperbolicity bigger than chi, whose trajectories do not approach the singular set exponentially fast, and whose trajectories exhibit some very weak sort of recurrence.
Okay, thanks.
Okay. The result for one dimension is slightly more complicated, because since we are in one dimension, we have non-invertible things. So first of all, first we have to consider the natural extension of this dynamics. And in the natural extension, we are able to get exactly, basically the same result as in my result with Mateus. So considering the natural extension, we are able for each chi bigger than 0 to code a big set, which is I call M0 hat, by a countable Markov partition, which induces a finite one and surjective coding.
Excuse me, you don't care about the structure of M0, geometry of M0, measure of M0?
No, I don't care. M0 is defined abstractly, independently of any measures. Then I observe that if the measure is adapted, and for example, if I know that Ruel's inequality holds, and the measure has Kolmogorov-Sinai entropy bigger than this parameter chi, then the measure is going to be supported inside M0.
Okay.
Okay. So it's an abstract subset in which the applications for measures come afterwards, provided you have tools to prove hyperbolicity and adaptability. And this is actually related to the next slide. So basically, most of our applications of these results are in the following way. If you get an ergodic equilibrium state of a Holder potential, then, and here is the drawback of the results. So the results, they do not give conditions to prove hyperbolicity, or they do not give conditions to prove adaptedness. But if someone comes to me and say, I know that this measure is hyperbolic, and I know that this measure is adapted, then the coding allows you to conclude that the lift of this measure in the natural extension, which is going to be the measure if the map is invertible, is either Bernoulli or Bernoulli times a rotation. And this is what I call Bernoulli up to a period. So this is this has applications also, in particular for the measure of maximum entropy, which is the simplest example of an equilibrium state. And because of this, we are able to use this structure of measure of maximum entropy to get, for instance, estimates on the number of periodic points. So as a consequence of this ergodic theoretical classification, we are able to count periodic points. All right. What I want to leave as a question to you today is exactly related to this hyperbolicity and adaptedness in the one-dimensional context. So can we get conditions to have, for instance, the validity of the Ruel inequality for these one-dimensional maps that I consider here? If we do, then as I said, whenever the Kolmogorov-Sinai entropy is bigger than chi, then automatically almost every point is going to have non-uniform hyperbolicity bigger than chi. So the first condition on the definition of M0 will be satisfied. And the second question is with respect to adaptability of measures. Can we prove that measures are usually adapted, just like in the case of Pshititsky? Or a weaker question, if we ask that the measures have large entropy, can we prove that they are adapted? So I recall you that Pshititsky, he did not assume breakpoints, so he did not assume discontinuities. So this question seems to be open whenever the one-dimensional map has discontinuities. If the conditions are found and they are satisfied, then we are able to apply the results. All right, so in part 3, I'm going to give a very brief sketch of the proofs. And for that, I start recalling you. It will be complicated for those who have never seen the method of pseudo-orbits of Bowen. But for those who have seen, this will serve as a sort of remind of what are the techniques involved in this method. So Bowen used this method to give a sort of new proof of, for instance, construction of Markov partitions for axiom A diffeomorphisms. And To do that, he considered what is known as a Lyapunov inner product. So if you have taken a course of hyperbolic dynamics, you might have heard about adapted metric. So the Lyapunov inner product is exactly this. It's a finite sum defined separately in the stable and unstable space. And because of that, it induces a chart, which is known as the Lyapunov chart, which allows you to see the dynamics of your map, just like the small perturbation of a hyperbolic matrix. And well, this is the second ingredient in the method of pseudo-orbit of Bowen. The third one is an easy observation, which is under uniform hyperbolicity, the splitting is continuous. So these charts, they behave continuously with respect to the point X. So one of them is close to the other whenever the centers are close. And then he used the notion of pseudo-orbits together with the notion of graph transforms, together with the idea of considering refinements of covers, which is due to him himself and Sinai. And plugging these 6 ingredients all together, he was able to give a different proof of the existence of Markov partitions for axiom-made diffeomorphisms. And we want to mimic this method. But when we try to do that, the first 2 initial conditions, which are that in the uniform hyperbolic situation, we have a splitting that is continuous, and we have a hyperbolicity that exhibits itself at every step, is no longer true. So the splitting is usually only measurable with respect to the point, and the hyperbolicity is only seen on the average, so as limits. And this makes it difficult to understand what are the candidates for Lyapunov charts, what are the candidates for saying that 2 Lyapunov charts are close. How do we bypass the difficulty that while in the uniform hyperbolic situation, the set of Lyapunov charts is with some metric compact, is another difficulty. And also another difficulty is how do we define a pseudo-orbit in the non-uniform hyperbolic situation? And some of these questions can be solved considering passing theory, which provides exactly the charts, the substitutes for Lyapunov charts that allow us to see the dynamics as a small perturbation of a hyperbolic matrix. And to define them, we change the definition of Lyapunov inner product, which was previously a finite sum, to actually an infinite sum. This is directly related to those 2 measurements of the quality of hyperbolicity that I mentioned to you in the definition of the coded set. Okay, so this allows us to define the passing charts, and provided we consider these passing charts in a very small domain, then we are able to see the map as a small perturbation of hyperbolic matrix. And this small domain, in the classical passing theory, it depends on the quality of hyperbolicity. It is actually equal to the quality of hyperbolicity to some negative power. So recall that I said that whenever the hyperbolicity is bad, this number is big. And this number being big means that this number raised to a negative power is very small. So this part here of the domain of the size says that whenever you have bad hyperbolicity, the domain of the passing chart has to be very small. This is the usual feature of passing theory, which in our context with the presence of singularities also has to take into account the proximity to the singular set. So because of that, we will actually take the domains of the passing charts, not only the quality of hyperbolicity to a negative power, but the minimum between this and the distance of the point to the singular set to, actually I put it wrong here, here should be a positive power. So whenever you are very close to the singular set, you do not want your chart to intersect the singular set, so you have to reduce it. And the proper way of reducing is raising this distance to a power and then taking the minimal with the other phenomenon given by the bad hyperbolicity. So the size of the passing chart is now takes into account these two phenomena, the non-uniform hyperbolicity and the proximity to the singular set. And the way that we require ourselves to say that two passing charts are nearby is no longer only requiring that the center of the charts are close to each other. Because since these things vary only measurably, we could have two very nearby points for which the splittings are very different one from the other. So this needs to be fixed, and this was fixed by Omri Sarig, which I should actually mention that most of this method is based on. And the way that he said that we should consider passing charts to be close was saying that you require not only that the points, the centers of the charts are close, but you also require that the splittings that you see in the 2 points are almost the same. And you also require that the quality of hyperbolicity that you see in each of these 2 red directions, each of these 2 blue directions are comparable. So this is saying that you are in a good situation, and this is saying that you have 2 nearby passing charts. If you get this new definition of nearby passing charts, and then you also have to define stronger notions of pseudo orbits, and then use graph transforms with this stronger notion, together with the usual Bowen-Sinai refinement, then you hope to mimic exactly what Bowen did and construct the Markov partition. But unfortunately, this is not enough. Because since you are dealing with a countable family, the refinement of a countable family can sometimes be uncountable. For example, the set of intervals with rational endpoints is a countable family, but its refinement is uncountable. So you need to control all of this construction in a better way. And in order to do that, you need to make a better measurement, a more precise measurement of non-uniform hyperbolicity, which unfortunately until now is not able to be done only using the passing charts. So Sarig introduced the notion of double passing charts, which is 2 passing charts with defined in 2 different domains and centered at the same point. And the idea here is that one passing chart is going to control the hyperbolicity in the stable direction, and the other passing chart is going to control the hyperbolicity in the unstable direction. So with this introduction of double passing charts, you are able to analyze separately the stable and unstable behaviors in the non-uniform hyperbolic situation. And this is quite reasonable in the non-uniform hyperbolic context, and that's why it has been successful, for instance, in this example of constructing Markov partitions. So once you define these double charts, which allow you to separate the analysis of future and past, you also need to control parameters with the correct balance. And the correct balance has 2 sides. In one side, this control has to be strong enough for you to have a good coding, but it has to be loose enough for you to have a good decoding. So it can neither be very strong nor very weak. Otherwise, you are going to have problems with the coding or with decoding. It has to be in between. Together with this correct balance, you also need restrictions on the codings that you allow. And since you are restricting the codings that you allow, you get a smaller subset of codes, and this allows you to have a easier decoding. So by restricting the coding, you have more chance to get a better decoding. And these restrictions are actually related to 2 conditions. One of them is, I already mentioned, is how to say that 2 passing charts are nearby. But the other one is requiring, and this is crucial, some maximality on these parameters PS and PU. So in some sense, PS and PU can also mean some choices of sizes for the stable and unstable manifold at the point X. And we expect in the uniform hyperbolic situation that if you iterate an unstable manifold, it grows at least a constant amount. So the maximality of these parameters is exactly related to this. We expect that whenever you have a possible transition, the next S parameter is at least e to the chi times the previous one. So this is maximality of the parameters. So putting all of these things together, how to precise measure non-uniform hyperbolicity, balancing the parameters in a correct way, and restricting the codings to some conditions, we are actually able to run the usual method of pseudo orbits of Bowen with the do changes and get the countable Markov partitions. I just want to finish with one extra ingredient which somehow is hidden in the proofs, which is which Mateus and I called it an improvement lemma, which in rough terms says that the dynamics improves the quality of hyperbolicity. And this is better explained with the following picture. So imagine that you have two passing charts, one centered at x0, another centered at x1, and you have a point x inside this passing chart on which you have an unstable manifold here. And the image of this unstable manifold, it's another unstable manifold passing through the point f of x. And as we expect in hyperbolicity, unstable manifold gets stretched under forward iterations. If you stretch, it means that you are in some sense smoothing out the possible variations inside this unstable manifold. And the improvement lemma exactly quantifies this possible variation. It says that if the quality of hyperbolicity at x divided by the quality of hyperbolicity at x0 is very big, so there is a big variation, then after you apply the map, things get stretched, things get more regular, and then the quality of hyperbolicity of the new point divided by the quality of hyperbolicity of the next center of the chart, it diminishes by a factor which is actually smaller than 1. So you would expect that if you apply this many times, then this quality of hyperbolicity will be very comparable between the point and the center of the chart. And using this allows us to prove that we are able to do a refinement and still get a cover that, not only a cover, but a partition that is going to have countably many elements. And this concludes the proof of the construction of the countable Markov partition. And it also finishes my talk. Thank you.
The applause is very complicated in this situation.
Sorry? Ah, claps.
Okay.
Lorenzo is in a not very optimistic mood.
Oh yeah, very optimistic mood today. You know. Well, I think that now it's time for questions. I don't know if there are some questions for Yuri.
Maybe Basan has more questions.
I have a question for you. What do you mean by quality of hyperbolicity?
I means that if it takes a long time for you to see the contraction in the stable direction, then you have bad quality.
Okay.
Right? Because
do you also mean like
I mean, it's
that it's
constant
not uniform?
Yeah.
I also mean what?
That good hyperbolicity would mean that you see the same amount or quality of hyperbolicity inside the little chart.
Yes, it's in the usual
same.
pressing theory is related to the constant that you see the contraction.
Yes. Can you go back to the penultimate?
Which one?
Yeah, this one. So what is the here? I mean, x0 and x. I forgot. I zapped.
So it is.
They are.
You have
How
to.
do you compare x0 and x? It's for any x0 and x, or for which?
Yes. So if you have this passing chart at x0, and this x is a candidate of a coded point, so it actually has to come from some more complicated things, some what we call generalized pseudo orbit. And you want to say that whenever you are coding, all the parameters of the coded point are almost the same as the parameter of the passing charts. So x is the coded point, x0 is the center of the passing chart.
But if you iterate, I mean, they split apart x0 and x.
Yes, so x0, x1 is not the image of x0.
What is x1 then?
X1 is a point nearby to x0. It's like a pseudo orbit. So you have a pseudo orbit.
You follow x.
Charts.
Okay.
Yes.
You follow.
And you have a coded point x.
So what is the reason here? Why does it improve?
Why does it improve? Because you see things stretching. That's the best crude explanation that I can give.
Yes. Okay. Fair. Okay.
Because the bad points left the neighborhood.
This is, I should say that it seems to me that this is similar to those estimates that people are recently doing in anisotropic Banach spaces when they want to prove Lasota-York inequalities.
Yeah.
So they use the improvement in these directions.
Yeah, in fact, because the representatives of x1 and f of x in the precedent chart will be closer in some direction.
Yeah, maybe I don't know.
When you had the picture of the surface with the red line, when you introduced the singularities, you can consider, what do you think of, what was this red line? I didn't understand.
This red line is a curve of, for instance, of points where you either cannot define your dynamics or points where the derivative is infinity. So it's places where the dynamics is getting degenerate.
Okay, like the singular points or the degenerate points in the one-dimensional case. Okay.
Yes, or the grazing collisions in the billiard case.
And can you treat singular flows like the Lorentz flow or similar?
No, so far we cannot. With Sylvain and Jérôme, we have a kind of more abstract, which I think it's more abstract way of coding three-dimensional flows, which the work is still not finished. We hope to finish. Well, I was planning to go in June to visit them, but my plans, they're all upside down now, so I don't know when this is going to happen. And we expect that the techniques will be more suitable for singular flows, but we just expect, we have no indications of that.
Okay, thanks.
More comments, more questions?
I have one question. Can we do some sort of 10 minutes coffee after the talks?
Sorry?
Coffee, 10 minutes coffee.
But we can do what you. I am very open to new ideas, Hannah. What is your proposal? Of course, we can do coffee, tea, cookies, champagne, whatever. I don't know.
I don't know. It's just a suggestion. If you like, so that we can talk freely after the talks.
First thing, I will stop the recording now. Okay.